In this example, we are implementing a thermostat control using a PID controller in a PLC program written in structured text. The program is developed in EcoStruxure Machine Expert HVAC, which is commonly used for programming Schneider electric HVAC controllers. The goal of this program is to demonstrate how to use the PIDAdvanced function block to control cooling in a more precise way compared to a simple on-off thermostat. Instead of switching equipment completely on or off, the PID controller produces a continuous output between 0 and 100%, which can be used to control devices such as variable speed fans, valves, or compressors. First, let's review the variables used in this program. We begin with the PID controller instance. PID_cooling PIDadvanced. This creates an instance of the PIDadvanced function block, which performs the PID control calculation. Next, we define the PID parameters. RKP real equals 4. This is the proportional gain of the PID controller. It determines how strongly the controller reacts to the difference between the set point and the measured temperature. UIT equals 100. This is the integral time, expressed in tenths of a second. The integral action helps eliminate steady-state error over time. UIT equals 0. This is the derivative time, also expressed in tenths of a second. Derivative control predicts the future trend of the error and improves system stability. In this example, it is disabled by setting it to 0. Next, we have the PID output variable. PID output, real. This variable stores the analog output of the PID controller, which ranges from 0 to 100%. The core of the program is the PIDadvanced function block call. The controller is enabled using Zen equals true. This activates the PID controller during every PLC cycle. The process variable is connected using RPV equals iSetPoint. This represents the reference value used by the controller. The setpoint input is connected using RSEP equals NTC_sensor. This variable represents the measured temperature from the NTC sensor. The controller operates in automatic mode. X manual mode equals false. This means the output is automatically calculated by the PID algorithm instead of being manually set. The hold function is disabled. X hold equals false. This ensures the controller continues updating the output normally. Next, we define the output limits. Our high limit equals 100.0. Our low limit equals 0.0. These limits ensure the controller output stays between 0% and 100%. We also define a small deadband. Our deadband equals I differential. The deadband prevents small temperature fluctuations from causing unnecessary control changes. Auto-tuning is disabled in this example. X auto-tune equals false. Instead, we manually configure the PID parameters. The proportional, integral, and derivative values are connected to the function block using RKP, UIT, UITD. Finally, the reset input is disabled. X reset equals false. After the function block executes, the PID output is read from the controller. Our PID output equals PID cooling analog. This value represents the calculated control signal produced by the PID controller. The output ranges between 0 and 100% depending on the temperature error. To summarize the operation of this program, the PLC continuously executes the PID controller during every scan cycle. The controller compares the measured temperature from the NTC sensor with the desired set point temperature. Based on the difference between these values, the PID algorithm calculates a control output. The proportional, integral, and derivative parameters determine how quickly and smoothly the system reacts to temperature changes. The resulting output is a continuous analog signal between 0 and 100%. This signal can then be used to control HVAC equipment such as a variable speed fan, cooling valve, or compressor capacity.